Okay, so this is the third portion of the week 2 lecture. As you can see on the screen, we are now combining the translation and rotation part together into a 3x3 matrix formulation by adding some zeros and one in the last row. So here you have Vx is Px plus cosine of theta and Vn minus sine of theta times V0. This is the same as this form right here. So what you see here is in fact what I mentioned to you, that you have a two-dimensional rotation matrix on a planar robot on x and y plane, and the last column is px and py, the coordinates of the v, n, and o coordinate system, the origin of that coordinate system. So here is the simple homogeneous matrix for translation in xy plane followed by rotation around the z-axis. This is typical homogeneous transformation matrix for quote-unquote planar robot which is working on only one plane. Okay, which is really not a true really robot, but the only thing close to that idea is for the end effector of a numerical control machine which works on a plane and moving around and cuts the metal. Okay, it's always on the same plane. It has to be there. Okay. So this is the transformation matrix. Now, in general, when you go to 3D, you are going to have a rotation around the z. This is for x, this is y, this is z. The 3 element corresponding to the z is 1, as I said before. Okay, you always have a 1 in the corresponding to the rotation axis around which you are rotating. If you're rotating around y, you're going to have a 1 in the y 2. And if you're rotating around the x, you have a 1 position. So this is a typo here. This should be Rx. Please remember that. I hope you print it. It has to be x. The last one is x. So rotation around the x-axis, y-axis, and so forth. All these operations you see in this lecture and all the lectures ahead of you, there's corresponding command in the toolbox in MATLAB. So you have actually Rx represented as a command, like a typical MATLAB command. Okay. We use the toolbox for homework, but we use Python and other things for the project. Okay. So, look at the top part of this. You see that the rotation matrix is 1, 1, 1. It's an identity matrix. But you have px, py, pz. That means I'm not changing anything. X remains in the same direction as before. When it moves, z same way, and y same way. The only change is that coordinate red has moved p units to the blue coordinate. That means the coordinate has moved in the x amount of px, in the y direction py and pz. Okay. Now here you have only rotation and no translation. You have these unit transformation, unit vector in x in 3 dimension of the 3 unit x component of the three unit vectors, n, o, and a, y component, and z component. This is the general representation of a rotation matrix. Okay. And you can, in fact, you can see later on that you want to go from A to B, you will have a set of parameters that are key about the configuration of the robot. We will call it Denowitz-Hartenberg parameters, or DH for short. Professor Denowitz and Professor Hartenberg were two mechanical engineering professors at Northwestern University in the 50s and early 60s, and they came up with those transformations, a combination of rotation around this, translation around that. In that combination will take you from one point to another. Okay, and those parameters associated with DH parameters, which you're going to see them in a minute, they come with as a spec sheet with your robot that you're going to buy for industrial use. It's like, for example, voltage rating or current rating and so forth. When you buy a robot, that parameters come with the robot. Okay. So, again, to repeat, you have a homogeneous transformation matrix H, which transforms your x, y, z coordinate into n, o, and a coordinates. And once again, you have a 3 by 3 rotation component, a 3 by 1 translation component. And for example, the first row, Vx, the x component of V, is going to have nx with Vn, ox, Vo, and ax, Va plus Px. The first three are the rotational component, and Px is the translation. Combination of translation and rotation, which brings the x component of the end effector at the very end. Okay. So the rotation and translation part can be combined into a single homogeneous matrix if and only if both are relative to the same coordinate frame. Obviously, it doesn't make any sense if it's more than one frame. It has to be one frame. Okay. You are moving in real world. You don't move. You're not working. Robot is not working in a virtual world. So, for example, let's look at this scenario. We want to find the homogeneous matrix. You have three coordinates, let's say three consecutive joints. Base, shoulder, and elbow, for example. You have a point in the N, O, and A coordinate system, the last one, the bluish one, showing in terms of this reddish vector, V and V over here. Point relative to the X, Y, Z. In other words, how can I show these three-dimensional coordinates, W's, in respect to the red coordinate system? Okay. As you might expect, it will consist of 1, 2, and 3 homogeneous transformation matrices. The red by itself has its own initial transformation matrix. In order to go to the green, it has to be post-multiplied by another 4 by 4 matrix to get there. And then at that point, you are at the green, you want to go to the blue, another one, 4 by 4 matrices. So the same point has this coordinate in IJK system, this coordinate XYZ, and this coordinate of NOA. You have one point in the free space, three ways to show with respect to three different coordinate systems. Okay? So W, I, J, and K with respect to this system is going to be pi, pj, pk, okay, which is here, plus the rotation matrix and b and b over. Okay, so given this thing that you want to reach, you pre-multiply by 3 by 3 rotation matrix, add a translation because you're going from here to here, that's p, pi, pj, pi, pj, pk. Okay. And then now that you are at wi, wjk, you can complete it by adding that padded with 0 and 1. So this is going backward, if you wish, from the blue to the green. That's what it takes you from there. From blue to green, going backward. And now you can actually go from ijk to xyz. You add a translation component to it, plus the 3 matrices. Remember that when you are at the very beginning, this is going to be your rotational matrix. You have 3 sets of unit vectors. So wx, wy, wz, the same point, that and keep up that point with respect to x, y, z, is going to be this rotation matrix times tx, dy, tz, the rotation component, times wi, wj. If I now combine them together, I multiply those 2 translation matrices. Okay, I'm going from given. Remember, for inverse kinematic, I know n, o, and a. I know where I want to go. I want to go back and see all the respective translation and rotation. I have to multiply this 4 by 4 to this by 4 by 4. Okay. By substituting for wi, wj, wk from the previous page. So, therefore, relation between wx, wy, wz compared to the end effector location or the end of the total translation and rotation, H is the transformation matrix. And it's going to be multiplication of those 2 respective matrices of their own. Now, you could separate the 2 together as you have seen before. You can first translate, then rotate. Translate, then rotate. You can do that too. You can do it in 4 steps, okay? Because it's all commuting together. Okay. Translation relative to XYZ frame, followed by rotation relative to XYZ frame, followed by translation relative to JIJK frame, and finally rotation relative to I. So basically meaning that you can go like this and then move here and then rotate again and move there. You reach the final place. Yes?
Can you do it more than 4 steps? Can you do maybe 6 or 8?
A question raised in the class, can you do it for more than 4 steps? 6 or so?
Exactly.
Yes, you can, depending on additional degrees of freedom. You can move on. You got 3 more to go for a typical 6 degree of freedom industrial robot. Okay. Absolutely. So that's what we just said. Rotation, rotate. So the homogeneous matrix is a concatenation of numerous translation and rotation. Okay. So you can, this is basically a text describing that you could also rotate first, then go to translation. You could commute between them. So let's now talk about forward kinematics. And we try to solve simple, trivial robot problems, two-link robot, on a plane. Similar to your double pendulum in the lab. Okay. You have a robotic arm that It starts out aligned with the x0 axis, would be here. And you tell the first link to move theta 1 and the second link to move theta 2. The question is, what is the position of the end of the robot arm at that point? Imagine that you have a situation like this, one plane, okay, I'm moving here, I'm moving there, where am I? That's what it is. Theta 1, theta 2. There are two different solutions you could have, geometric and algebraic. This is probably easier solution, very simple, because you're dealing with two triangles, okay? And then if you look at this, the x component of this is going to be this L times cosine of theta 1 added L2 times cosine of this angle. Cosine of this angle. So you basically look the trigonometric relation that you know for how to find the based on the largest side of the triangle and the angle which makes with the direction you want. The first thing is the exception. The angle is measured relative to the initial position, which is 0. When this robot is lying down on this axis, is 0 angle. For robots with more links and whose arm extends into 3 dimensions, the geometry gets much more tedious and much more difficult. That's why beyond a 2-link robot, you need to go to homogeneous matrices and keep multiplying. So that was one of the reasons I also asked all the students, including North Carolina students, to go, even before the first session, go to appendices in the backup book by Dr. Cork to review and freshen up on matrix manipulations and some of these Jacobian matrix linearization is there. All of those are there, and it may even be useful for you for your homework number 1. You need to learn how to linearize a nonlinear equation in the form of a linear equation. Okay. In algebraic coordinate transformation, you have involved coordinate transformation, which is similar to what you already know. You multiply a 3 by 3 matrix, which involves a 2 by 2 rotation matrix, a bunch of 1 and 0s, and 2-dimensional translation component, px and py, or delta x, delta y. So let's look at this example. You have a 3-linked arm that starts out aligned in the x-axis, like this. And each link has a length L1, L2, L3 respectively. You tell the first one to move BBY1 and so on. I'm not sure if BB is the mistype or not. First one to move by Y1. Yeah, I think this is supposed to be Y. So it's BY. Okay. Anyhow, your first link, as you see here, is going to move Y1. Okay, the first. The second one is going to move Y2 here. And the third one is going to move Y3. So you have 3 rotational operation here. And all 3 of them are coming out of the plane of this diagram, namely the Z component. Z1 for this, Z2 for this, Z3 for this. Your homogeneous transformation matrix is going to be a combination of rotation first times the translation of x1 along E, rotation around for y2 around z, then translation x2, which is this, of L2, and then rotation of y3. And this is the end effect. This is the end of this combination of translation rotation. That is to say, you rotate by y1, which puts you in the x1, y1 frame, x1 and y1 frame. Translate it along the x1 axis by L1. You reach here. You rotate y1, it puts you along this link, and then you move x2 by L2 into x2, y2 plane, and so on until you reach the x3, y3 frame. The position of the yellow dot here relative to x3, y3 frame is L3 and 0, because that point has no component in the y coordinate. It's just going to be here L3. L3 being the length of this last link. So it's L3 and 0. Multiply h by that position vector will give you the coordinates of the yellow point relative to the xy. So when you reach this point, all you need to do is to multiply this vector in 2 dimensions by the H matrix to come up with the coordinate of the yellow coordinate. That's it. This is a typical forward kinematics issue. You keep moving, translation, rotation, one after another in particular order, then you end up with a point which you say, I know where I am now. Okay? Unfortunately, that problem has limited usefulness in real application of robotics. Inverse kinematics is the one that has a lot of usefulness, because it is, end effector is in the Cartesian space, in a Fourier space, is handling something. You may have a human arm here, for example. You know, some of you are helping Berat print a lot of 3D printer, a lot of limbs of a human and robot that we are about to order, a couple of them, to this company. And hopefully will arrive sooner than later. And Berat team they are not waiting for the robot to arrive. They're printing before the robot arrives, because we have all the CAD files for the parts of the robot, including the hand and the effector, and face and legs and whatever you have. So we may hopefully watching that robot walk at the end of semester. Okay. So there are a lot of things cool about this course. There are a lot of nice things that we're gonna, I think, enjoy together. So a slight variation of the last rotation make the yellow dot the origin of a new coordinate system. So let's now actually have make that dot to be the coordinate of the fourth coordinate system, which is right at the edge of Cartesian space. In that case, the h going from here to here is rotation y1, translation L1, rotation y2 at the second joint, followed by the translation of L2, and then rotation of y3, and then one translation L3, which is the length of the last link. And this is the complete homogeneous transformation of this yellow dot, the tip of your end effector in the real world, in real space, Cartesian space, with respect to original. The position of the yellow dot relative to x, y coordinate is of course 0, 0. It's sitting on its own coordinate, origin. We know that. Notice that multiplied by 0, 0, 1 vector, they equal to the last column of the H matrix. x, y, z is 0, 0, 0. So that's the last one. So we want to go next to the Denhaven-Hartenberg parameters, and we will do that in the next last section. Okay? Take another break.